In this video, we're going to be talking about independence. Now, sometimes the knowledge that one event has occurred does not change our assessment of the likelihood that another event will occur. Consider the genetic trait hitchhiker's thumb, which is the ability to bend the last joint of the thumb back at an angle of 60 degrees or more. Now, whether or not an offspring has hitchhiker's thumb is determined by two random events: which gene is contributed by the father and which gene is contributed by the mother. Which gene is contributed by the father does not affect which gene is contributed by the mother. These are independent events. Let's consider that a bank offers different types of loans. So the bank offers both adjustable rate and fixed rate loans on single-family dwellings, condominiums, multifamily dwellings. The following table, called a joint probability table, displays probabilities based on the bank's long-run loaning practices. Take a look at the data now. So what is the probability of an adjustable loan? Here we see that it's a total of 0.70. Let's continue with this. What is the probability of an adjustable loan given that it's a condo? Here, we'll take our adjustable for a condo divided by the total condos. So 0.21 divided by 0.30 will give us a value of 0.70. Knowing that the loan is for a condominium doesn't change the probability that it's an adjustable rate loan. Therefore, the event that a randomly selected loan is adjustable and the event that a randomly selected loan is for a condo are independent. Independent events are two events knowing that one will occur or has occurred, but it does not change the probability that the other event will occur. So two events, E and F, are said to be independent if the probability of E given F equals the probability of E. Now, if the probability of E given F is the probability of E, then it is also true that the probability of F given E will equal the probability of F. If two events are not independent, they are said to be dependent events. Other types of independent events would be flipping a coin twice, or rolling a six-sided dice twice. The first roll won't affect the second roll, and on a coin flip, your first flip doesn't affect the outcome you could get on the second flip. The multiplication rule for two independent events. So if you have two events, E and F, and they're independent, if and only if the probability of E and F, or the E intersected with F, equals the probability of E times the probability of F. Let's go back to the hitchhiker's thumb. So again, suppose that there is a 0.10 probability that a parent will pass along the hitchhiker's thumb gene to their offspring. What is the probability that a child will have a hitchhiker's thumb? This would happen if the mother contributes a hitchhiker's gene, or H+, and if the father contributes a hitchhiker's gene, H+. So we want to know what is the probability that you get an H+ from mom and an H+ from dad. Since these are independent events, we just multiply the probabilities together. So we would take 0.1 times 0.1, which would give us a 0.01. So the multiplication rule for k independent events. So let's say that we have multiple events, so E sub 1, E sub 2, all the way to E sub k, and they're all independent. Now, if the knowledge that some number of the events have occurred doesn't change the probabilities that any particular one or more of the other events occurred, we can do this. So we'll have the probability of E sub 1 intersected with E sub 2, intersected with all the way through E sub k, That's just going to give us the probability of E sub 1 times the probability of E sub 2 all the way up to the probability of E sub k. This relationship remains valid if one or more of the events are replaced by their complement, not E. Let's go a little bit deeper with this. Now, suppose that a desktop computer system consists of a monitor, a mouse, a keyboard, the computer processor itself, and storage devices such as a disk drive or a jump drive. Now, most computer system problems due to manufacturer defects occur soon in the system's lifetime. Purchasers of new computer systems are advised to turn their computers on as soon as they are purchased, and then to let the computer run for a few hours to see if any of the problems occur. So we're going to let E sub 1 equal the event that a newly purchased monitor is not defective, E sub 2 equal the event that a newly purchased mouse is not defective, E sub 3 equal the event that a newly purchased disk drive is not defective, and E sub 4 equaling the event that a newly purchased processor is not defective. So suppose that the four events are independent, with E sub 1 equaling, the probability of E sub 1 equaling the probability of E sub 2 at 0.98, and the probability of E sub 3 equaling a 0.94, and finally the probability of E sub 4 equaling a 0.99. So we want to know what is the probability that none of these components are defective. So we're going to take the probability of E sub 1 and E sub 2 and E sub 3 and E sub 4, and we're able to multiply those together, giving us a 0.98 times 0.98 times 0.94 times 0.99, which equals a 0.89. So in the long run, 89% of such systems will run properly when tested shortly after purchase. Let's go back to our information. So we want to know what is the probability that all of these components will run properly except for the monitor. So we're going to take the probability of the complement of E sub 1 and E sub 2 and E sub 3 and E sub 4. So what we're going to do is we're going to replace the probability of our E sub 1 with its complement, which is 0.02. So we'll have 0.02 times 0.98 times 0.94 times 0.99, giving us a 0.018. Let's look at a different example. So suppose I pick two cards from a standard deck. So this can be done in two ways. Remember that a standard deck has 52 cards. I can pick a card at random, replace the card, and then pick a second card. Sampling with replacement, that means that the events are typically independent events, because I've put the card back, which means I theoretically could get that card again. But I could also pick a card at random and not replace it, and then pick a second card. Sampling without replacement, the events are typically dependent events, because if I took the ace of spades and I didn't put it back, how can I possibly get the ace of spades again? So if I pick two cards from a standard deck without replacement, what is the probability that I select two spades? So we want to know, are the events E sub 1, which is that the first card is a spade, and the event E sub 2, that the second card is a spade, are they independent? Well, the answer here is no, because I did not replace my card. So if I'm taking the probability of E sub 1 and E sub 2, then I need to find out the probability of E sub 1 and then multiply that with the probability of E sub 2 given that I got E sub 1. So I'm looking for the probability of a spade given that I drew a spade on the first card. That's what that second piece right there is saying. So the probability of drawing a spade is 1 in 4. Because out of the 52 cards, there are 13 spades, and that reduces to 1 over 4. And I'm going to multiply that with the probability that I got a spade on my first pull. Well, if there's 13 spades and I took one, there's only 12 spades left. And if I started with 52 cards, and I kept one, there's only 51 for me to draw on the second time. So when I multiply 1/4 times 12 51sts, I'm going to get 1/17. Let's go ahead and do another example. Suppose the manufacturer of a certain brand of light bulbs made 10,000 of these bulbs and 500 are defective. You randomly pick a package of 2 such bulbs off the shelf at a store. What is the probability that both of your bulbs are defective? So we want to know, are the events E1 and E2 independent, where E1 is the first bulb is defective and E2 that the second bulb is defective? Are they independent? Well, to answer this question, let's explore the probabilities of these two events. So what would be the probability of selecting a defective light bulb to begin with? Well, there were 500 defective ones out of the 10,000 made, which means that we have a 0.05 chance that our light bulb is defective. So having selected one defective bulb, what is the probability of selecting another without replacing it? Well, instead of having 500 defective bulbs, because I already have one of them, I only have 499. And there's no longer 10,000 bulbs, there's only 9,999, which gives me a chance of 0.0499. Now these values are so close to each other that when rounded to 3 decimal places, they're both 0.050. So for all practical purposes, we can treat them as being independent. If a random sample size n is taken from a population of size capital N, then the outcomes of selecting successive items from the population without replacement can be treated as independent when the sample size n is at most 5% of the population size capital N. Let's go back to our light bulbs. What is the probability that both bulbs are defective? Are the selections independent? We're going to go ahead and assume that they're independent based on what we just saw. So we're looking for the probability of defective and defective. So the probability of a defective bulb is 0.05, and the probability of getting the second defective bulb is 0.05, which is going to equal 0.0025. So we have a 2.5% chance of that happening. Oh, sorry, I have a 0.25% chance of this happening.